Hello, math humans. We're going to do 6.2 today. We're going to be talking about differential equations. In addition, we're going to be solving differential equations around growth and decay. So as we just jump in with our first example, I want to solve the differential equation. So we'll get our brains turned back on just by doing a regular diffie equation first. Remember that I'm going to do my separation of variables. I like to rewrite y prime, and I'm going to write it as dy over dx is equal to 2x over y. And then the next step is I'm going to move my variables by cross multiplying. So I'm going to get y dy is equal to 2x dx. Now, when you're doing these problems, you need to always make sure, A, that you show this step. Actually, you may not have to show this step, but you need to show this step. This one's very important. On an FRQ, oftentimes you get a whole point just for doing this step. It's called separation of variables. So now I'm going to integrate both sides. On the left-hand side, I get y squared over 2. On the right-hand side, I get 2x squared over 2 plus c. The 2's cancel, and so I get y squared over 2 is equal to x squared plus c. I want to lose the y, or lose the 2, and so I'm going to get y squared is equal to 2x squared. Technically, I'm going to multiply the constant by 2 also, but 2 times a constant is still a constant, so we just still write plus c. So this would be my general solution because I have a plus c. If I wanted to find the particular solution, they would have to give me an initial value for x and y so that I could solve. It is sufficient to leave your problem as y squared because technically you've kind of solved for y, and then you don't have to worry about the plus or minus. So I would recommend that you stop here for the general solution. Alrighty, for our next example, we're going to start introducing kind of our interesting new topic for the day. So for example 2, again, we're going to solve the differential equation because that's what we're doing. And I'm going to get y prime is x times 1 plus y. That's a plus in case you can't read my scribble. So again, I'm going to start by rewriting, and I'm going to write dy over dx is equal to x times 1 plus y. I'm going to do my separation of variables and move these guys at the same time. So I'm going to get dy over 1 plus y is equal to x dx. And I'm going to do u substitution for this one, so when I get ready to integrate both sides, I'm going to show you that u is equal to 1 plus y. My du is dy, so I don't have to introduce anything. So on the left-hand side, I'm going to get the natural log absolute value. 1 plus y is equal to x squared over 2 plus c. So this is where the problem gets a little bit entertaining. I need to solve for y. It's in log form, so to solve for y, I'm going to go back to exponent form. So I'm going to do that right here because I'm running out of room. E to the x squared over 2 plus c is equal to 1 plus y. Okay, and the general rule of thumb at this point is that we lose the absolute value when we go to here. Okay, I'm going to rewrite this side by using my properties of exponents. So I'm going to write y plus 1 is equal to e to the x squared over 2 times e to the c. I'll explain why this is important in a sec, but the properties of exponents show that if the bases are the same, I add the exponents, which is what happens here. And so now the part about this that is unique is e raised to the c is still a constant, so we're going to replace this with c, and so then my equation is going to become y plus 1 is equal to c e to the x squared over 2, and then y is going to equal c e to the x squared over 2 minus 1. And this would be your solution. The new trick is this part right here, so going from this situation to replacing e to the c with c, because e raised to a constant is still a constant, and so then we manage and call it a c, and we pull it out front, okay? So then this is going to be an exponential growth or decay problem based on the way that the formula is written, which is why we talked about today we're going to bring in growth and decay. Alrighty, let's do another example. So for example number 3, again we're going to solve the differential equation. And in this one I have dy over dx is equal to 6 minus y. So technically on this one I can't do a separation of variables because this guy has to have something to multiply by. So I'm going to convert it and say dy is equal to 6 minus y dx. Now I'm going to move this. So I get dy over 6 minus y is equal to dx. I'm going to integrate both sides, okay? On this one, I'm going to go ahead and show my u substitution. So I'm going to write u is equal to 6 minus y, so my du is a negative dy. So I need to introduce a negative. So my integration is going to become a negative natural log absolute value 6 minus y is equal to x to the first plus c, okay? And I'm actually going to move this negative over here. So now I have the natural log of 6 minus y is a negative x plus c. I'm not going to make c negative because a constant is a constant. So at this point, I'm going to have a negative x, okay? So now what I need to do is I need to still solve for y. I'm going to go back to exponent form. So e to the negative x plus c is going to equal 6 minus y. I'm going to show this step again. Eventually we'll get to the point where we can skip it. So this is going to equal e to the negative x times e to the c. Remember we just call that c. And so I'm going to get 6 minus y is equal to c e to the negative x. And negative y is c e to the negative x minus 6. And then y is going to equal a negative c e to the negative x plus 6. So a couple of things to notice about the algebra. Up here I chose not to make it a negative c, right? We'll notice that by the time I solve for the problem, c still ended up being negative. So the math tends to work out. And so this would be my particular solution. Actually, I lied. It's still a general solution, because I still have a c as part of my equation. And again, to solve for c, they would have to give me an initial condition that allows me to solve for c. Another thing to notice about this equation, this is an exponential growth or decay because I have e raised to the x. Okay, and so then now what we're going to talk about are our growth and decay models. So as we talk about growth and decay, in pre-calc we learned that we have y is equal to ae to the kt, and k is the constant of proportionality. That's a long word. A is the initial amount of whatever is growing or decaying. And then T, of course, is time. Okay. Well, when we go to calculus, we change a couple of the variables and we would write it as y is equal to c e to the kt. K is still the constant of proportionality. C is going to be the initial amount. It's also the constant that would come from solving a differential equation. Okay? If K is greater than 0, this is a growth equation. And if K is less than 0, this is a decay problem. Okay? All right, the next content that we want to do is a review from pre-calc. And we're going to talk about variation problems. Okay? And I'm just going to do, this will technically be our fourth example, but I'm going to use it to teach some content as well. So if you have words that say the rate of change of y is proportional, I think I have, okay, I'm okay, is proportional to y. It looks weird, but I'll explain this in just a moment. So the rate of change of y, rate of change always means derivative in calculus, woohoo, right, is proportional to y. Is proportional to means that I'm going to have a k times y. So remember our direct variation and inverse variation problems from last year in pre-calc. When time is equal to 0, y is equal to 2, and when time is equal to 2, y is equal to 4. What is the value of y when t is equal to 3? So we're going to go ahead and write an equation. Notice that they give you 2 points, and I'm going to manage that first. So I have the point 0, 2, and then I have the point 2, 4. The variables can be confusing, but remember time is always an independent variable, which means it goes in the first position because you can't change time, right? And so then this would become the dependent variable. Okay, so I have 2 data points when I start. Now I'm going to write my equation. So unlike problems that we did last year, this is the new piece, okay? The rate of change of y. So I'm going to write dy over dx, there's the rate of change of y, is directly proportional to ky. Now k is different than c. C is the constant that we get when we integrate. K is the constant of proportionality. So there are 2 different types of constants. So if I'm going to find the value of y when t is 3, I need to have a model for y. Well, if I need to have a model for y, that means I need to solve the differential equation. Okay, so I'm going to separate my variables, and I'm going to get dy divided by y is equal to k dx, and then I'm going to integrate both sides, and so I'm going to get the natural log absolute value of y is kx plus c. So remember, this is a constant, and then this becomes my constant of integration. I'm going to go back to my exponent form, e to the kx plus c is equal to y, which is equal to c e to the kx. So basically what we've just done is we've developed the growth model equation using some calculus. So that's cool. Alrighty, so there's our model. Okay, so now I need to find both my k and my c. So I had an initial condition of 0, 2, so I'm going to write 2 is equal to c e, and then here's my k, and then multiplied by, 0, which is polite because e to the 0 is going to be 1, so I know that capital C is equal to 2, okay? So now my model has morphed a little bit, and I'm going to write my new model up here. So now I'm going to have y is equal to 2 e to the kx. Now I need to solve for k, so I'm going to use the second point. 4 is equal to 2e to the k, x is 2. So 4 divided by 2 is 2, is e to the 2k. So 2k natural log e is the natural log of 2. The natural log of e is 1. K is going to equal the natural log of 2 divided by 2. And this is going to be approximately 0.3466. If you wanted to be more precise, you could leave k as the natural log of 2 over 2. Alrighty, so we're still not at the point, now we're finally at the point where we're going to answer the question, what's the value of y when t is 3? And you couldn't see that, but it's up at the top of my page. My bad. So my model is y is equal to 2e, and I'm actually going to write the natural log of 2 over 2 times x. Okay, now I want to predict what y is, so y of 3 is going to equal 2e to the natural log of 2 divided by 2 times 3. And when I do that math, I get approximately 5.657. Okay? And then I think we can just stop there, and then I would write to report my solutions approximately, because I rounded 5.657. So that was actually kind of cool, because we developed, using calculus, the formula that we're talking about for exponential growth and decay. All right, so for half-life problems, they're a unique type of problem. So half-life problems, last year in pre-calc, we learned the model y is equal to a b to the x divided by the halving time, because it's a half-life problem, okay? But in calculus, we can still use ce to the kt. I will tell you that if you use this equation for a half-life problem, the math is easier, but I'm going to do it with this one just to complete our last example. So for example number 5, we're going to have 10 grams of the plutonium isotope, and I'm going to write it, I'm hoping this is correct because it's been a long time since I took chemistry, was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? All right, so if we manage some of the information that we're given, 10 grams is going to be our starting point. So at time is equal to 0, we're going to have 10 grams of the plutonium isotope. So I'm going to have the data point 0, 10. Okay, so I'm going to start with my equation. Y is equal to Ce to the Kt. Oh, I also am going to tell you that the half-life of plutonium-239 is going to be 24,100 years. And the book acted like we're supposed to know that number. I don't know that number, so I'm just going to give you that number. So if I go back to here, I need to solve for C, so I'm going to substitute in my initial point. So I'm going to get 10 is equal to Ce to the K times 0. This goes to 1, so I get C is equal to 10, which makes absolute sense because they told us we started with 10 grams of plutonium. So my model is Y is equal to 10e to the kt. I didn't have to do this, but I just wanted you to see that you can develop it easily and quickly if you need to. All right, so the half-life is 24,100. I still don't know K, so I'm going to use the half-life. So I'm going to set up another equation. So 10 divided by 2, so that would be half of the initial amount, is equal to 10e to the K, and the half-life is going to happen every 24,100 years. So the goal at this point is to solve for K. So I'm going to divide both sides by 10. So I get e to the 24,100k is equal to a half. I'm going to go back and use my properties of logarithms. So I'm going to get 24,100k natural log e is equal to the natural log of a half. And in case you don't remember the graph, so there's my graph of a natural log. This value is going to be negative because it's before 1, which means that it's a decay problem, which is good because it's just confirming our math. This is 1, so k is going to equal the natural log of a half divided by the 24,100. And that's going to be approximately, it's a big number, negative 0.123428761. Alrighty, so now at this point, so I bring back my computer. Hate it when it stalls like that. Now I have enough information to write the model. So the model is y is equal to 10e to the negative 0.123428761 times t. And it wants to know, my original problem was, how long will it take the 10 grams to decay to 1 gram? So I'm going to substitute in a 1 equals 10e to the negative 0.123428761 t. The goal is to solve for t, so I'm going to divide by 10. 1/10 is equal to my e to the negative 0.123428761 t. I'm going to go to the next page. I'm going to take the natural log of both sides, so I get a negative 0.123428761 t is equal to the natural log of 1 over 10. And then my time is going to equal the natural log 1 over 10 divided by the negative 0.123428761. And when I solve for t, did I write it down? Oh, I didn't push buttons on my grapher. So it's going to equal a number, and that will be your number. I guess I should do that. That would be polite. So I'm going to do the natural log of 1 divided by 10. I was a slacker. Divided by negative 0.123428761. Go. And I get that it's going to take, such a long time, 80,059.285 years. Oh, my goodness. Alrighty, that was quite the number to discover. Thanks for playing today. I'll talk to you later. Have a good day.